Now we're going to look at the proofs of a couple of the things. We're not going to prove everything. We're going to prove a few things. All right, so first we're going to look at this uncertain state model where we have this kind of uncertainty. That is, the norm of delta is less than or equal to 1. And so we have this theorem. The uncertain system is stable for all delta with the norm less than or equal to 1, if and only if there exists a positive definite P that satisfies this linear matrix inequality. All right, so how do we prove all of this? Okay, so in order to do this, we first use a lemma, an intermediate result that can give us some traction for this problem. So for any element, the lemma says this: for any element delta in our uncertainty set, we have this inequality is satisfied. So notice delta appears on this side of the equation, not on this side of the equation. Okay, so this is the lemma. The proof of this lemma follows: since delta is in S, then the norm of delta transpose delta is less than or equal to the identity, or actually that matrix is less than or equal to the identity in a positive definite sense. So if we multiply both sides of the inequality by HP on the right and HP transposed on the left, we get this inequality. Okay, so you can actually treat matrix inequalities that way. So we notice this side now is in terms of the uncertainty. This side is not in terms of the uncertainty. And notice we have this term here that looks an awful lot like that. Okay, guess where that's going to come from? So if I now look at this quantity here, I have this quantity times its transpose. So that as a quantity is positive semi-definite. Okay, if I go ahead and do the matrix version of FOIL on all of this stuff, I get these four terms. Okay, so so notice I have G transpose, but this is being transposed, so this is just GG transposed. Here I'm going to get G times this. Here I'm going to have this transposed times G transposed. That's this. And then we have this last term over here. Okay, and we use this result to give us this inequality. Okay, we use this result to give us this inequality. Okay, I have delta transpose delta here, and I don't have it here. So that's where so all of this is positive semi-definite. Okay, if I take these two terms over to the other side of the equation, I get exactly this inequality. Okay, so and the reason it works is because delta is of norm less than or equal to 1. Okay, so that's why all of this comes out. So now it's like, what's all this? Where is this coming from? Well, we're going to see. So notice we have G delta H, which is part of this. So that's the uncertain term in our A matrix. Okay, and here we have the transpose of that same kind of term. So that's important. All right, so our theorem said this, and so somehow we're going to need to come up with this linear matrix inequality and P positive definite and so forth. Okay, so we've introduced this lemma. Let's move on to the proof. Okay, suppose that such a P exists. Then the linear matrix inequality is satisfied if and only if, first of all, negative I is negative definite, which is obvious, and the Schur complement is negative definite. Okay, so the Schur complement of this inequality. So I have this being negative definite, and then the Schur complement of this being negative definite, which is all of this stuff, plus, because I have a minus here, this quantity transpose times this. Okay, and that must be negative definite. Okay, so we have this inequality is satisfied if the P exists and that linear matrix inequality is satisfied. By the previous lemma, we know that delta is bounded, and the fact that delta is bounded, we have that these two terms are greater than or equal to these two terms. Okay, and so if this inequality is satisfied, then this inequality is definitely satisfied. Okay, so we've used the lemma, and we've used this inequality to give us this inequality. And we now have A naught and this that I can group together with P on the right and factor out the P. I have this and all of this. So when I take the transpose of this, I'm going to get P on the left. I can factor out P on the left, and I get this. So this is A transpose, and this shows this quantity now is negative definite. And so this is since P is positive definite and this is negative definite, by Lyapunov theory, we have stability. We have A is stability for any uncertainty in the uncertainty set. Cool. That's the sufficiency side of this. So I won't prove the necessity side of it. It's just more complicated. But the bottom line is that I can always find a delta that if, and generally you prove it by contrapositive argument. That is, for any delta that's of norm less than or equal to 1, if that inequality is not satisfied, then we can find a delta that makes the uncertainty make the system unstable. So anyway, the sufficiency is the main part of the proof anyway, as far as I'm concerned. The necessity, not so much. But anyway, I won't go into all the details. I won't bore you with all of the details. All right, let's move on to the next proof. So that was the stability problem. Now we have the state feedback problem. So the uncertain system can be stabilized for all delta in the uncertainty set if and only if there exists a P positive definite and a matrix Y that satisfies this matrix inequality. Now, one of the differences between this theorem and the other theorem. In this theorem, it is not required that A naught be stable. A naught does not have to be stable. In the stability problem that we had before, A naught had to be stable. Okay, so what happens here now is we're actually trying to stabilize the system. Okay, and so because of the way things are written out, this quantity with the Y here and its transpose makes it so that A naught actually doesn't have to be stable. So this is actually a true stability type problem. Okay, so this is what we have. All right, how do we prove this? So for any delta in the uncertainty set, I have this lemma. So this lemma is comparable to the lemma we had in the previous problem. And so I have all of this stuff and its transpose less than or equal to all of this stuff. And we notice this is very similar to the lemma we had before. The difference now is instead of just having HP, we now have HP plus CY to deal with, because we have uncertainty both in the A matrix and in the B matrix. So I'm going to define HP plus CY to be F. And so clearly, because because delta is in this uncertainty set, then I have this inequality. And so now if I look at this quantity, and actually I'm going to go through and show pretty much just exactly the same thing that we had in the previous lemma. So I have this quantity times its transpose, and so that as a quantity is positive semi-definite. I go through and do the FOIL, and I get this, and I notice that by this inequality, this is less than or equal to that, and so actually this should say less than or equal to that. But the important thing is that all of this is positive semi-definite. Okay, so now for the proof of the uncertainty problem. So if such a P and Y exist, then Y is equal to K times P. In the linear matrix inequality, again, we have this as part of that inequality, and also the Schur complement. The Schur complement gives this. Okay, the Schur complement gives this. So now we want to relate this to the stability of the problem. So I have this huge old hairy, and I'm talking hairy, matrix inequality. Oh, if you think this is hairy, you haven't seen anything yet. Okay, well, anyway. Here's this inequality that we have. All right, So with this stuff in here, I can go through and show that this inequality with the lemma implies this inequality. So notice that this involves the use of delta. The delta is in here. Okay, so I now have this inequality. So this inequality is independent of delta. This inequality now involves delta. And so we have all of that. And now I'm going to set y equal to k times p. Okay, so in here I have y and y. This is transpose. Here I have y and y. So I'm going to substitute y is equal to k times p. And when I do, I get this. I notice that I have a p on the right here, a p on the right there, and p on the right of both of these guys. Here I have p on the left, and I actually have p on the left of both of these guys. So I can factor that out this way. And when I'm all done, I actually get all of this stuff. I can actually boil it down till I get this. What is this? This is the state feedback gain for the system with uncertainty. And what this shows now is for p positive definite, this being negative definite means that a plus bk is stable for all uncertainties. Okay, because remember that uncertainty is embedded here in a and b, and so the uncertainty is contained in here, and what this shows is that this matrix is going to be stable for all uncertainties. So we have the structured uncertainty problem. So like I said, things can get really complicated. I'm not even going to bother to prove the discrete time result for both stability or state feedback design. It's way more complicated than we really want to get into here. And it would not edify you. That is, it would leave you overwhelmed instead of feeling like, yeah, I got this. So we'll pass on that. We're now going to move on to some practice problems.